Hello Year 13, this is Mr. Toll, and today we're going to be working through chromatography, which is one of the later topics in your course. Okay then, right, let's get started then. So today we're going to be looking at three different types of chromatography. The first of which is thin layer chromatography, sometimes known as TLC, not to be confused with the late 90s, early 2000s girl band. This is the one that you're used to, where you get the chromatography plate and put it into the solvent. So you'll recognise that one straight away. We're just going to go into a little bit more detail on how the compounds separate. Then we're going to be looking at something called column chromatography, which involves a glass column. It looks a little bit like a burette, and that's about purifying organic compounds. And then finally, we're going to be looking at something called GCMS, which is a pairing of two techniques, gas chromatography and mass spectrometry. You probably haven't come across this one before. And just to reference where we're at in terms of the specification, we're on 3.3.16 or page 65 as of 2020 on your specification, and these are the learning objectives for this lesson. Okay then, so let's have a look to begin with at thin layer chromatography, or TLC. Now, the first thing we do is we get a chromatography plate. This is not made out of paper anymore. The one you did at GCSE is made out of paper, but what this is it's a glass or a metal plate, and it's covered in either a thin layer of silica, which is silicon dioxide, or alumina, which is aluminium oxide. And that's our stationary phase. It looks a little bit like this. You've probably seen them in the lab before. They come in this little plastic box. The back of them's a shiny metal, and then this front side is almost a powder coating of that silica or alumina. First thing you're going to do is get a ruler and a pencil, and you're going to draw a baseline around 1 centimetre up from the bottom there. Call that our baseline. Now, what might you use TLC or thin layer chromatography for? Well, essentially what you're trying to do is separate a mixture and then potentially identify the components of that mixture. So I've drawn a little protein over here, and you might want to know what amino acids are in that protein. So the first thing you're going to have to do is hydrolyse it. And the way we hydrolyse proteins is with 6 molar aqueous hydrochloric acid. So that's a concentration of 6 moles per decimetre cubed aqueous hydrochloric acid, and if you reflux that for 24 hours you're going to get a mixture of amino acids, because you're going to hydrolyse all the peptide bonds, known as chemists as amides. You're going to hydrolyse all of those bonds, and you're going to end up with a mixture of all the different amino acids that protein was originally made from. Then what you're going to do is take a glass capillary tube, so that's like a really thin tube, and you're going to dip it into your mixture of amino acids and then spot that mixture onto the baseline of your chromatography plate. And as you can see there, I've put a little M underneath to mark that that's my mixture. Now, if you're going to identify exactly which amino acids were in this protein, you're going to need to compare it with some known reference standards, and you can buy these from a lot of the chemical suppliers. So R1 might be a particular amino acid, I don't know, alanine or something. R2 might be a different amino acid. Glycine, R3 might be another amino acid, cysteine for example, but all of those are completely pure reference standards of the amino acids. Most amino acids come as solid powders actually, so we'd probably have to make them up into an aqueous solution to begin with, but then we could spot those on the baseline in turn as well, so we can compare the substances from our mixture of amino acids with these pure reference standards. So then what we're going to do is get a beaker or a jar, and we're going to fill it with a solvent or a mixture of solvents that we're going to call our mobile phase. Typical solvents we use are things like ethanol, maybe methanol, ethyl ethanoate, which is an ester of an ethyl group and an ethanoate group, so that'll be the ester of ethanol and ethanoic acid. You can use petroleum as well, different mixtures of petroleum. And depending on how soluble your compounds in your mixture are, you're probably going to use a certain ratio of a mixture of solvents to get the separation just right. So then you're going to put your chromatography plate into that jar. It's important to remember that the solvent must not submerge the baseline, otherwise the compounds in each spot will actually dissolve outwards into the solvent and will never travel up the paper. You'll probably also want to put a lid on this and put it in a fume cupboard, because those solvents a little bit toxic by inhalation, so you're probably going to do this in a fume cupboard as well. So then what happens is, as the solvent runs up the chromatography or TLC plate, your compounds that were originally spotted down on the line here, they all move at different speeds up the plate, and therefore they separate out. You can see that our mixture here is separated out into two spots, so there must have been two substances in the mixture. That's the vertical separation there. And we can see that some of these pure reference standards here, they've horizontally aligned. I'll talk more about that in a moment. Okay, so once you've ran your chromatography plate, you're going to take the lid off, do all this in a fume cupboard, and then immediately what you're going to want to do is, you can see it's still wet from where the solvent's run up it. You're going to want to get a ruler and a pencil again, and you're going to want to draw your solvent front on the top of that chromatography paper. It's important that you draw that on before the solvent dries, otherwise you're not going to know where the solvent line went up to. So we call that the solvent front. Then we're going to dry it off. Probably dry it using a hairdryer. I normally do, hold it with some tweezers and dry it off with a hairdryer. Now, we've encountered a problem because we had these lovely spots that had travelled up our paper, but actually things like amino acids, you would have never even seen those spots in the first place. They're colourless. So you've got a chromatography plate now that's undeveloped. You can't see the spots. So I'm going to talk a little bit now about how we can develop the chromatography plate so you're actually able to visualise the spots and the separation that's occurred. So the first method you can use is you can get a UV lamp. I did actually draw that. I'm quite proud of that little diagram. So you can use a UV lamp, and quite often your compounds will be visualised by that UV lamp. So if I run the UV light over the chromatography plate, then as that light's shining on the spots, you'll be able to see them. So holding the light above each spot, you'll be able to get a pencil and draw a circle around each spot whilst the light's on it, and then you'll end up with a chromatogram with the dots outlined via the pencil marking that you drew on there. An alternative method, if you don't want to use UV light or your compounds are incompatible with that method of developing the TLC plate, is you can use iodine. And one of the interesting facts about iodine is it changes directly from a solid into a gas state. We call that sublimation. So if we get a jar and put some crystals of solid iodine, iodine's a grey solid, we put them in there, we put a lid on top. Now, iodine is sometimes called a locating agent because it lets us locate our spots. If you begin to heat up this jar again, probably with a hairdryer or something like that, then the iodine's going to sublime and it's going to give off this purple vapour. So iodine's a grey solid and it gives off purple vapour. And the iodine's essentially going to stick to the compounds and locate them by staining them. Okay, so we can now see the spots have appeared. We don't need to draw around them with pencil straight away, but it's worth doing as soon as you can, because although they're stained for a short period of time, if you leave that for about a day, those spots won't be located anymore. The iodine will just sublime away again. So we need to make sure that we do actually draw around those spots pretty quickly, but not immediately. Okay, so then we've got our chromatography plate, and we can see that we've outlined where the spots are on the chromatography plate, and we need to be able to analyse the chromatogram now. Now, the key way that we normally analyse a chromatogram is by calculating RF values. RF stands for retention factor. RF values of each spot, because we want to see how much the spots have been retained by the paper itself, or the chromatography plate, sorry. And the RF value is as simple as work out how far the spots travelled from the baseline. So we're going to measure with a ruler distance from the baseline to distance to the middle of the spot. You can see I've drawn a little dotted line there because sometimes these dots or spots are oval shaped, so we need a consistent means of measuring them. So we're going to measure to the centre of the spot, or the middle of the spot. And then we're going to divide that by the distance travelled by the solvent. So baseline to solvent front is that distance there. So if I measure these two values, I measured them in millimetres. So we can see that this spot, the first spot of our mixture, has travelled 29 millimetres, and the distance between the baseline and the solvent front is 105 millimetres. So if I calculate that now, I get an RF value of 0.28. Now, I've actually calculated the RF values for every spot you see here on this chromatogram. The first spot of the mixture, as we just calculated, was 0.28. The second spot of the mixture was 0.52. And then what we can do is calculate the RF values for all of our pure reference standards as well. And you can see that I've got some RF values for each of those. Now, if we look at this RF value for the first spot of our mixture, this one over here, we can see that this RF value of 0.28 is exactly the same as the RF value of the reference standard amino acid number 3. Okay, so we can see that this spot of our mixture and the reference standard number 3 have exactly the same RF value. Well, that makes sense because they both travelled the same distance up the paper. They horizontally align. That means they must be the same thing. Okay, so we know that our mixture contains the amino acid that is the same as whatever the amino acid number 3 was here, reference standard number 3. We can also see that the second spot of our mixture, this one here, has the same RF value as whichever reference standard amino acid R2 was. Okay, so there's the second spot of our mixture. There's R2. They horizontally align, so they must be the same thing. But we can see that this reference standard, R1, whatever it was, is not present in our amino acid mixture. So we can infer that that protein didn't contain this amino acid. Let's have a look at how we could write a written explanation for interpreting the chromatogram. So the first thing to state is how many substances are in your mixture. So here's our mixture, and it's separated out into 2 spots vertically, so therefore we had a mixture of 2 amino acids. It's very unlikely that a real protein would only contain 2 amino acids, but in this case it's a simplification. So that's the vertical separation from its placement on the baseline, and we can see that it's a mixture of 2 substances. We can say that the first spot of the amino acid horizontally aligns with the reference standard for amino acid R3, so therefore they must be the same thing. They've also got the same RF value, which proves that. The second spot of our amino acid mixture horizontally aligns with the reference standard for amino acid 2. They also have the same RF value, so they must be the same thing, so we know that our mixture contains that particular amino acid. And then finally, we always state a negative result in this as well. Our amino acid mixture, this here, does not have any horizontal alignment with whatever reference standard amino acid number 1 was. Okay, let's have a look now at explaining why the mixture separates in the first place. So you saw that we had our mobile phase, the solvent, or our mixture of solvents, and our stationary phase, which was the coating of the TLC plate. Okay, so the silica or the aluminium oxide, I went American just then, the aluminium oxide coating layer. And actually our separation is going to depend on how quickly each spot or substance that causes a spot moves up the paper. So it's all about the speed at which they move up the paper. So they're going to move at different speeds up the paper, and that's going to depend on how soluble they are in the mobile phase and their affinity for the stationary phase, how much they stick to the solid support there. Okay, so let's talk a little bit about that solubility in the mobile phase. So if our compound's really, really soluble, then it's going to move faster, so it'll travel further, and vice versa is true for that. So here's an example. What I've done is taken the chromatography paper, and we're viewing it from the side, and it's laid flat. So these are the compounds at the baseline here, and they're both in the mixture at the moment, so they're at the same point. So imagine that original spot here. We're just looking at it from the side. We can see we've got substance 1, and substance 1, the blue one here, is going to be really soluble, and substance 2 is going to be less soluble. Okay, and there's our baseline. So as the solvent moves up the paper, we can see that this substance here is really soluble in the mobile phase, the solvent, so it's going to travel faster, so it's going to move further, whereas this substance here was less soluble, so it didn't travel as far. Let's show you that again quickly. Less soluble substance in the mobile phase, moving slower, so travels less distance. More soluble substance in the mobile phase, travels further because it's moving faster. Okay, let's have a look now at this idea of affinity for the stationary phase. All affinity really means is how much it's attracted or adsorbed, with a D, not absorbed, adsorbed, okay? So if you're really heavily adsorbed, then you're going to stick to the stationary phase. You're going to be really attracted to it. So that means you're not going to travel very far because you're not going to move very fast if you're constantly sticking and dragging along this stationary phase. If you have a low affinity for the stationary phase, then you're not going to stick to it much. You're not going to be that attracted to it. You're not going to be very strongly adsorbed. So therefore you're going to travel faster. So you can see here that our blue dot didn't have a high affinity. It had a low affinity for the stationary phase, so it was weakly adsorbed, not very attracted, so it moved faster. Whereas this one here, the red dot, had a high affinity for the stationary phase. It was very strongly adsorbed, very attracted, so it travelled slower and travelled a shorter distance. Okay, so if you want to pause the video here, have a look at these questions, then come back to the video and answer these questions for me. Thanks very much. Okay, so let's go through the answers to this video now, these questions in the video. So, first question was, what does TLC stand for? You should have got thin layer chromatography. Next question, what's the stationary phase in TLC? Well, we're going to have a thin coating of silica, silicon dioxide, or alumina, aluminium oxide. And that's on a solid support material such as the plate itself, which is either glass or metal. Okay, what's the mobile phase in TLC? That's going to be a solvent or a mixture of solvents, typical examples given there. Conditions for hydrolyzing proteins, it's important that you know this. They are 6 mole per decimeter cubed aqueous hydrochloric acid, and you need to heat the protein at reflux for 24 hours to produce a mixture of amino acids. Next up, in TLC, what do we compare our mixture with? Well, we compare it with pure reference standards, which we spot on the baseline. What 2 options do we have for developing the TLC plate so the spots are visible? Well, the first is shine a UV lamp over the plate and draw around the dark spots that you see with a pencil. And the second is to place it in a jar with iodine crystals, heat the jar so the iodine crystals sublime, and then the iodine vapour will stick to the compounds locating the spots. You might want to add to that, draw around it with pencil, because the spots that appear due to being stained with the iodine vapour will eventually dissipate. There is a third example, which I haven't seen come up in an exam question in quite a while, but it's called ninhydrin. It's basically like an aerosol can that you spray straight onto the plate, and it develops the spots straight away. You then draw around them with pencil because that dissipates over time and the plate goes blank again after a few hours. Okay, next question was, what is the equation for RF? Very straightforward, distance travelled by the spot divided by distance travelled by the solvent. Where do we measure the spots? Right in the middle. How do you know that 2 spots are the same substance? Well, they'll have the same RF value and they will horizontally align on the chromatogram. The chromatogram is the developed TLC plate. Which 2 factors affect the distance travelled by the spot? We should have solubility in the mobile phase. Let's expand on that. If compounds are more soluble in the mobile phase, they'll move faster and therefore will travel further and vice versa. And we have affinity for the stationary phase. If compounds have a high affinity for the stationary phase, then they are strongly adsorbed, attracted, so they'll move slower and will travel a shorter distance and vice versa. Okay, let's move on now to the next variant of chromatography. Or not, let's answer the last question, which was the method question. Okay, right, so I've asked you here to write a method for determining which amino acids are present in a protein. So I'm going to leave my method up here for you guys to have a look at. Pause the video and then we'll go back to it. Okay, so as I said, now we're moving on to our next method of chromatography, column chromatography. So this one will be wholly new, I hope. Okay, so column chromatography, it's a technique that we use to purify organic compounds. Now imagine you'd carried out a reaction where you're trying to produce an organic product. Well, you're going to end up with an organic reaction mixture, and in that organic reaction mixture, you're likely to have the organic product that you desired, which I've shown by these blue dots here, and then you've probably got some kind of impurity. Now that impurity might be one of the reagents you used, but it could also be some unreacted starting material. And as a chemist, you always want to purify your organic product so you can carry on doing further reactions, or you can use that compound for its intended purpose. What you're going to do in column chromatography is take a glass column. And this glass column looks a little bit like a burette. It's essentially the same as a burette, except it has a little scintillated funnel at the bottom of it here to stop any solids that we pack the column with falling through. And secondly, it tends to be a little bit wider than a burette. It still has a tap on the bottom though. If we were to look inside this glass column, we will have packed it with a stationary phase, and that stationary phase will be a slurry. So that'll be a solid that's been suspended in a solvent, essentially. It's a slurry. So imagine wet sand on the beach. And that's either of aluminium oxide or silicon dioxide. So previously we coated the TLC plate in aluminium oxide or silicon dioxide. This time we're taking the pure powder and making a slurry out of it, and we're filling the column, packing the column full of that. So what we're going to do is pour our organic mixture, reaction mixture, on top of the column, and it will sit on top of that stationary phase. So we'll have our solid mixture waiting on top of the stationary phase there. Then what we're going to do is pour our solvent continuously through the glass column. Now what that's going to do is it's going to force our reaction mixture to move through the stationary phase. But what you can see there is the blue dot came out first and the orange dot, our impurity, came out second. Now that's obviously going to be dependent on the nature of your mixture, whether your desired product comes out first or your impurity comes out first. That will completely depend on the nature of your mixture. But this separation is due to pretty much the exact same reasons that we obtained separation with TLC. But this time we don't talk about RF values or retention factors. We talk about retention time, how long the compound spends in the column. And this is again due to solubility in the mobile phase and affinity for the stationary phase. So this blue dot here is going to be highly soluble in the mobile phase. So it's going to have a really short retention time because it's going to move very quickly through the column because it dissolves really well in our solvent. It's probably, this blue dot as well, which moves through really quickly, it's probably got a really low affinity for the stationary phase. In other words, it doesn't absorb to the stationary phase very much, so it passes through the column really quickly. Our orange dot, our impurity, whatever substance that is, it's probably not very soluble, so it doesn't dissolve well in the solvent. And it's probably got a high affinity for the stationary phase. It absorbs very well to the stationary phase, so it's going to spend longer in the column, so it's going to have a longer retention time. It's going to stay in the column for longer. So let's have a look at that again. So as you can see there, each compound eluted from the compound at different times, had different retention times due to their different solubilities and affinities for the stationary phase. Okay, what we need to do then is pause the video here, answer these questions in your Google Doc, then come back to the video to see if you got the answers correct. Okay, let's go through our answers then. So what does CC stand for? You should have got column chromatography. What is CC used for? Purifying organic compounds. What is the stationary phase in column chromatography? You should have gone for a slurry of solid aluminium oxide or silicon dioxide. Remember, we're not dissolving the aluminium oxide or silicon dioxide, we're purely making a suspension of it, and that creates a slurry. Next question, what's the mobile phase in column chromatography? That's going to be a solvent. Again, it could be a mixture of solvents in a given ratio. How do we measure separation in column chromatography? Retention time. That's how long it takes to leave the column, elute from the column. What will affect separation in column chromatography? Solubility in the mobile phase and affinity for the stationary phase. Some more detail here as well. Okay, so now what we're going to do is have a look at gas chromatography and how gas chromatography can be combined with mass spectrometry. So gas chromatography is used to separate mixtures, but it's also used to identify the components in that mixture. And there's a couple of different methods of identification, which we're going to look at. But typically gas chromatography is combined with mass spectrometry to create this combined technique that we call GCMS. Here's a visual example of what's going on, and I'm going to detail that a little bit more now. So the first thing that we have in GCMS is we inject our sample mixture into the GCMS and we vaporize it as well. Okay, so it has to go in as a gas, and for this reason typically we use GCMS for compounds which have low boiling points, quite volatile compounds. Now the vaporized sample is actually carried through the column with an inert carrier gas, and that's actually our mobile phase. So either helium or nitrogen, an unreactive carrier gas, is going to be our mobile phase, which carries this vaporized sample through the column. Here we have our column, and you might notice that it's a metallic tube essentially that's been coiled up, but it's hollow, and the inside of it is packed with our stationary phase. This time, however, our stationary phase is a solid, or it's a solid coated with a viscous liquid. Just to be clear here, this viscous liquid is the stationary phase that's coating our solid, okay? And we also put this column inside a temperature controlled oven. Now there's two things going on here. The first thing we do with our column is we coil it up to save space. Otherwise that column would have to be really long and the whole device would have to be really, really long and it would take up too much space. So by rolling the column up into this coil, we can actually end up with a really nice and long column to maximise the separation, but take up a short space. We also put it inside a temperature controlled oven because if we heat it up, we can actually get the compounds to separate out a little bit faster. The gas chromatograph, this first part of the device, also has a detector built in. And this detector builds a little graph for us. And this graph tells us retention time. So here's our time. And the detector's waiting. And you can see at 5 minutes here, it detected something eluting from the end of the column. The area underneath that peak is proportional to the abundance of that sample, compound within the sample. Okay, and you can see here we've got 3 major peaks. This first peak here is probably the solvent coming through that the compound was originally dissolved in. But we can see we've got 3 major peaks here, and the area underneath those is going to be the abundance. But then as the compounds exit the gas chromatograph, we also pair up a mass spectrometer. And that mass spectrometer is able to produce a mass spectrum of the compounds and provide us with MZ values, which enable us to identify those substances quite readily. So here's an example of an application of GCMS. You might have someone that's suspected of taking steroids, like this dude here, and we might want to take a blood sample of him and see whether or not his blood sample contains those steroids. So I'm going to inject the steroids into the gas chromatograph. Remember, they're carried by a carrier gas. I haven't shown it here. And we can see that there's 3 major compounds that have come up. And they're going to pass through the column, but they're going to pass through the column at different speeds due to their different solubilities in the mobile phase, so how well carried they are by the carrier gas in this case, and their different affinities for the stationary phase, in this case the viscous gel that coats the solid support material inside the column. So they're going to move at different speeds. So we can see that we've got red coming out first, then blue, then yellow, whatever they are. Okay, and this is going to generate a spectra of retention times in this case. So we can see that we've got 3 major compounds coming out, and we can see that the area underneath this first peak at a retention time of 5 minutes is the highest. So we've probably got the most abundance of whatever this first one was. Then we've got the second one, smaller abundance, and the third one, even smaller abundance there. Now, you might be able to compare these retention times with known values of retention times if you're constantly looking at the same things. So if you're constantly looking at testosterone, for example, you might know that testosterone elutes at 5 minutes. So you might go, oh yeah, he's definitely taken testosterone, so he's cheated on whatever test he's done there. So retention time might be a good way of simply identifying those compounds straight away. However, you may wish to carry out further analysis using a mass spectrometer. And that will really enable you to truly identify what that person has taken, for example. So you might know that 288 grams per mole is a key indicator of testosterone. So the mass spectrum there gives you a little bit more of a clearer indication that you've truly identified that compound. Okay? So typical examples of GCMS include determining the identity or level of alcohol and drugs in blood or urine. Also, if you've got some historic artworks which require restoration, you may wish to work out which paints were originally used, and that will GCMS will enable you to analyse which paints were in a painting, for example, and you can use the correct paints for your restoration. So again, here's an example of a chromatogram from gas chromatography, and this will be running the whole time, so you'll see the graph live. And we can see that at 3 minutes we've got a peak, 5 minutes we've got a peak, and I don't know, 7.5 minutes we've got a peak there. So here we can see the area underneath each peak represents the abundance of each different substance. Each one of these peaks is a different substance, so we've detected 3 substances in our mixture in this ratio of abundance, and their retention times could be used to identify them. But if 2 samples had exactly the same retention time, if 2 substances in your mixture had exactly the same retention time, then you might not truly be able to identify them. If we increase the temperature in the oven, then all of these peaks would just shift to the left, because we'd get shorter retention times for all of them. Sometimes though, if you shorten the retention time, it results in the peaks overlaying, which is a little bit annoying. So a better way of doing this is to pair it up with a mass spectrum, and the results from that mass spectrum can easily be compared with a database, which can automate the identification of whichever substances are in your mixture. Okay, so if you want to pause the video here, give these questions a go for me, and then come back to the video to have a look at the answers. Okay then, so what does GCMS stand for? Gas Chromatography Mass Spectrometry. What is GCMS used to analyse? Identity and quantity of alcohol and drugs in blood and urine, or different paints for art restoration purposes. What data does GC give us? Tells us the retention time and the relative abundance by area under the peak. What data does the mass spectrometer give us? It gives us the MZ value from which we can calculate MR, and we can also calculate the relative abundance from the mass spectrum. Suggests the identity of the inert carrier gas, should be helium or nitrogen, sometimes they use argon as well. How can the mass spectrometer be used to automatically identify a component? Well, we could compare the mass spectrum data with a database of known compounds to automatically identify that component. And a key limitation of using gas chromatography on its own, well, if two different compounds had the same retention time, you wouldn't be able to identify them from that alone. So you'd need to follow it up with mass spectrometry. Okay, so that's the end of this video, guys. Thanks very much for watching. Please make sure you've put your answers in the Google Doc and submitted it if you've been requested to do so. Otherwise, I hope you found this video very useful, and I'll see you in the next one.